All right, welcome to a really quick note session for average rate of change for AP Precalculus. Before we get into anything crazy, let's just talk about what average rate of change is. Basically, it's saying we might have some weird function like this, but I have, these two x values, and I want to find what the average rate of change is here. Obviously, here is different than here, which is different than there, but on average, what is my rate of change? So really what that is it's just saying I'm going to take this point and this point, so that would be f of a as a y value, and then, well, f of b, so I'll extend my axis up here, as a y value. And what I'm going to do is I'm going to draw a straight line. And this line here is going to represent our average rate of change. So what the formula that is it's essentially the rise over run. This is slope that we did eons ago in Algebra 1. So slope was given as the change in y over the change in x, or, as we talk about it, f of b minus f of a over b minus a. You might have talked about in algebra y2 minus y1 over x2 minus x1. This is just a lower level version of this. This is going to be used in all of AP Precalculus as well as all of AP Calculus. This is still valid. It's just not going to be as commonly used. So once again, what this represents is the slope of the straight line between 2 points. So these are two coordinates. Once again, that b value is an x, this is a y, x, y. So it's the slope between these 2 points. It's that straight line. So average rate of change, you need to burn this formula into your brain. I will never once give it to you on a test or quiz. It's going to be used a lot. So we need to make sure that we are fluent with average rate of change. F of b minus f of a over b minus a. Now, if you're solving and you decide to do f of a minus f of b over a minus b, that is okay. The only difference is your work is going to look different than your friend sitting next to you who used this, but you're going to get the same answer. As long as these a's and these b's line up, that's fine. So, for example, something that is not good is if I did f of a minus f of b over b minus a. That's no bueno. You can see here that the a's and the b's don't line up. They're diagonal from each other. That's no good. So either one works. I'm going to reference this one because that's what most of the literature says. So what's kind of the applications here? Let's take a look. The idea here is that we want to use it to estimate how much things are changing. And then we can also go one step forward with what's in the blue and find what is happening at an instant. So let's read. The rate of change at a point A, so it's like this point, is given by the slope of the tangent line. So remember, we talked about tangent lines. That's the slope at a point. So the tangent line touches once, so that's about the slope. If I want to look at the slope here, at this x value, it would be something like this. Now, in blue is what's the kicker. This is what's important. We can estimate a tangent, we can estimate a tangent line and its slope by finding an average rate of change over a small interval. So we're going to see what this looks like in a half a second. We're going to be given a table, and we're going to have to do some math with it for a value that we don't exactly know, but we can estimate over a small interval. So let's go ahead and look at an example of these two. So let me move this over here. Let's keep the notes up top. So what I want to do is I want to find, first, let's just look at this table. So I have time and I have my output. So I have my input of time, and I'm given these values, and it's kind of weird. I get 0, 2, 5, 9, and 10. I don't give like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then I also am given some outputs. I think this is heat, so it's like as the day goes on, something cools off or something like that. Who knows? So what I want to do is find the average rate of change over a 10-minute interval. So what I'm going to do first is I'm going to set up the fact that delta y is equal to delta x. I like writing this. Some of you guys might write the f of b minus f of a. I guess I could write that too. So f of b minus f of a over b minus a. And for the first few times that I do these, I'm going to plug in stuff on that 10-minute interval. So the 10-minute interval, it starts at 0 and it ends at 10. So that's going to kind of be like my my b value and my a value, if that makes sense. So I'm going to plug in f of 10 minus f of 0 over 10 minus 0. So now, f of 10, what I got to look is the function value at 10. So that's 43. So 43. I'm next going to look at f of 0, which is the function value at 0, so 66, over 10 minus 0. 43 minus 66 is going to be negative 23 over 10. So my average rate of change over that interval is negative 23 over 10. The next piece is going to be talking about and referring to this blue. So what I want to do is estimate the instantaneous rate of change when t equals 5, or 3.5. So obviously 3.5 is somewhere here. I don't have any values, but I know we can estimate a tangent line. And what does the tangent line show? The tangent line shows the instantaneous rate of change. So let's make that note here. Instantaneous rate of change, tangent line shows. So I'm going to find, as this blue text, hello? Why is this not moving? As this blue text tells me, I'm going to find the average rate of change. So I'm still going to use this formula over a small interval. The smallest interval next to 3.5 surrounding it would be from 2 to 5. So that's what I'm going to do. I'm going to do f of 5 minus f of 2 over 5 minus 2. I'm finding the average rate of change over this tiny little interval here. And by plugging stuff in, I'm going to get 60 minus 52 over 3. So I'm going to get 8 over 3. That would estimate my average, or excuse me, my instantaneous rate of change, because I'm over a small interval. In theory, if I made this interval even smaller and smaller, it would get better and better. That's a calculus topic. That's something that we're also going to talk about a little bit this year in limits. So the next thing we're going to do is answer these two questions. So we did it with a table, finding average rate of change, but now we're going to do it with given like a function, and then we're also going to explore a graph. So we're kind of going to hit all three representations in this to kind of give you a taste of everything. So I want to find the average rate of change of this function from negative 1 to 4. So that average rate of change, I'm going to have f of 4 minus f of negative 1 over 4 minus negative 1. So what f of 4 means is I just take 4 and I plug it on in here. So I'm going to, like I said, for the first couple, write everything out. So 3 times 4 plus 4, and maybe some guys could see what that value is going to be right off the bat. 3 times negative 1 plus 4, and then 4 minus negative 1. That'll equal 5. So looking here, this is going to equal 12. I got 3 times 4 plus 4. Oops. So I'm going to get root 16 minus, and then negative 3 plus 4 would be root 1 over 5. So this is going to equal 4 minus 1 over 5, or 3/5. So once again, we're just using multiple different representations to be able to find the same thing. We're always looking for this average rate of change. It's not rocket science what we're doing here. The next piece is going to be interesting. We're going to look at this graph over here, and we're going to estimate some of these rate of change. And I want to rank it from high to low. So I'm going to color code this because I'm going to draw stuff up on that graph to estimate the rate of changes. So first and foremost, I want to find the average rate of change between 0 and 3.5. Remember, the average rate of change is just literally a straight line between the y values of 2 points. So the y value at 0 is here, and the y value at 3.5 is about here. So what I'm going to do is I'm just going to draw a straight line between those two y values. So we can see that that slope is positive, but it's not very positive. Next, let's look at the IROC, instantaneous rate of change. So what that would be is just the tangent line, the slope of the tangent line at 1. So whenever I have a min or a max, that tangent line is going to be flat. So we can see already kind of how these slopes are going to interact and compare. The instantaneous rate of change at 2. So looking here, I see I go from concave down to concave up. So I know this slope is going to be that point of inflection. So it's going to be super negative. It's going to be super negative. The fun fact that we know about the point of inflection is it has the steepest slope. In this case, it's the steepest negative slope with the points around it. So it's going to be super negative. And lastly, average rate of change from 0 to 1. So I'm going to start at 0, end at 1, and all I do is I draw a straight line. So now all we got to do is just rank these from high to low. Our highest slope was obviously that average rate of change on 0 to 1, so that's going to be our first one. Then the next highest slope is this one here, so that's going to be our 2. Oops, our 2. Instantaneous rate of change. This flat one is going to be a 0, and then this one's going to be some like really big negative numbers. So we're going to have 3, then 4. So ranking from high to low. I should say like ranking slopes from high to low. But yeah, so all this is doing is, reinforcing our idea that the average rate of change with these 2 points, it's literally just a straight line between two y values. And the instantaneous rate of change is the tangent line. So if you could walk away from this knowing those two facts, that average rate of change is the straight line between the 2 points, instantaneous rate of change is a tangent line, and then of course this formula here and this idea, those are the main 4 points. We're going to talk about one more thing just very, very briefly so that we could talk about it come Monday. And that is the following. So, linear functions. So we've talked, or not we, you've probably talked about linear functions for a while now, maybe so far as back into 7th and 6th grade. All it is something that looks like y equals mx plus b. That's a linear function. You have a y and then equals some sort of stuff with an x with no power, or excuse me, not no power, it has the power of 1. So it's just an x by itself. It's not squared, it's not cubed. So let's go ahead and read. Rate of change in linear functions is constant. So that's going to be important to note. We are constant. From y equals mx plus b, the slope is that rate of change. This m value never changes. It stays constant. It's, for example, like y equals 2x plus 3. This is our rate of change at all times. It never changes. So if the rate of change never changes, it's always 2, then we could say the rate of change, this number, the slope of the rate of change. Oh, excuse me, I misspoke. So how the change changes, which is going to start to get a little bit confusing. We're looking at this m value. It doesn't change ever. We're looking at the rate of change of it. It doesn't change. It's always 2. So the rate of change of the rate of change, so of m, is 0 because it never changes. So what we can concur is that the slope isn't ever changing. There's no concavity. and it's just a straight line. So for example, I mean, this is throwback to eons ago, but 2x plus 3, we're looking at something like we start up 2, and then, or excuse me, up 3, and then our slope is 2. So you're looking at something like that for 2x plus 3. So we can see it's a straight line. There's no concavity, and the way in which it's changing, all the tangent lines forever, they're all exactly the same. The rate of change of the rate of change is 0. This sentence here is very confusing. I'm not going to deny it, but we need to learn how to be able to read stuff like this and get a fluent understanding of what's going on. So that's it for today. Real simple average rate of change. We'll talk about it